Now, not everything is supremely as beautiful and symmetric as the circle, but some things try to be. Take a look at this shape. It's a regular polygon. It has 6 sides, and so it's kind of circular-like, except all the sides are flat, but they're all the same. So we're going to assume this is a regular one, so they're all the same size. All the angles are the same, for example. I want us to figure out the area. Well, finding the area for this can be done in a very simple way, because you see, if you think about it, we have a whole bunch of triangles. Here's the very center. And so really, you see that we actually have 6 triangles. And we know the area of a triangle is 1/2 base times height. The base is always going to be 10. And we just have to find the height. That's the big mystery. So now, it turns out, here is the formula for the area of any regular polygon, where we know P represents the perimeter. That's the sum of all the sides, which is kind of like, looking at all the different bases we have, all these different triangles. And we multiply that by 1/2 A, where A is the distance from the very center, perpendicular distance to the center of one of the faces. Okay, so it's just basically taking all the triangles and adding them all up, and that's where the perimeter comes from. So in this case, we have 6 sides, and so we know that each, since it's a regular polygon, we know that each angle here has the same number of degrees measure, so it's 120. And this is half of it, so this is actually 60. So this is 60, and this is 60, and that forces this angle to be 60, so it's an equilateral triangle, which means equiangular, and it's a theorem that all equiangular triangles are also equilateral triangles. And so, in fact, we know that if this is 10, then this has to be 10, and this has to be 10. And now if I drop this perpendicular length, I know that I have a 30, 60, 90 right triangle. I could use the Pythagorean theorem. This cuts it in half. This is 5. So this length right here is half of 10, which is 5. And so I know 5 squared plus a squared equals 10 squared, and we can solve that. Or you can recognize that we have a 30, 60, 90 right triangle, and so this is going to be just 5 square root of 3. So this length here is 5 square root of 3. So, the area, for all that work, is given by this formula, 1/2, that length we just found, 5 square root of 3, multiplied by the perimeter. So the perimeter isn't just 10, it's going to be 10 plus 10 plus 10 plus 10 plus 10 plus 10, also known as 60. And so let's see, 60 divided by 2 is 30. 30 times 5 is 150 square root of 3. That's the exact answer. If you plug that into a calculator to estimate, you see 259.8 centimeters squared. And so there we have an estimate, numerical estimate, to the area of this cool thing. Let's try one more. All right. The octagon. The stop sign. 3 feet each side has. It's a regular one, so all angles are equal and all sides have the same lengths. How many degrees does each angle have, by the way? Well, let's see. If you think about it, I can cut this up into a quadrilateral, another quadrilateral, another quadrilateral, and I happen to remember that the sum of the angles of a quadrilateral is 360 degrees. And I've got 3 of them, 1, 2, 3. So that's 3 times 360 degrees, which is 1,080 degrees. So the total sum of the angles is 1,080 degrees, which are evenly distributed amongst these 8 different angles. So I divide by 8, and I see that every one has a measure of 135 degrees. Okay, 135 degrees. I take a look at my picture. And this might be a little bit small. You know what? I think I might actually just enlarge that triangle so you can sort of see what I'm doing and what I'm writing here. So just enlarge to show detail. I'm going to still call this 3. And now, you see, since I know that the entire angle here is 135 degrees, and this is going to be half of it, since all these triangles are congruent, I know that all the angles are going to have the same measure, so therefore this angle plus that angle, they're the same angle, and they have to add up to 135, so half of that is going to be 67.5. And now, if I drop down this perpendicular, I know that this length is half, which is 1.5. And I can figure out this angle right here, this little teeny sliver of an angle, because I know that it's complementary to this one, because this is 90, this is 67.5, and so the sum of the angles have to be 180, so these two have to add up to 90, and so that leaves me with 22.5. These are degrees, by the way. Degrees for that. Wow, we're doing a lot of little technical work here. I'm after this length. How can I find that length knowing the opposite side and this angle? Well, I can use a trig function. And what trig function should I use? Well, I know this angle, I know opposite, I want adjacent. Sounds like tangent. So see how tangent actually ends up coming into this question about areas? It's all connected, folks. Here we go. So we have that the tangent of 22.5 degrees equals opposite 1.5 over this adjacent A. If I solve this for A, you could either take a cross product thinking about the tangent 22.5 over 1, or you could multiply everything through by A. Any way you want. We solve, we get A equals 1.5 divided by tangent of 22.5 degrees. So that length is given by that very complicated number. Okay, and that's in feet. Now, if you want to find the area, we just apply this formula. And we say that the area equals 1/2 this complicated number we just found, 1.5 divided by tangent of 22.5. And I multiply that by the perimeter. Well, that's going to be 3 times 8, which is going to be 24. All right, and if we simplify this a little bit, what we see here is if you take 1.5 multiplied by 24 and divide by 2, we see just 18. So I see 18 over tangent 22.5 degrees. So that's the exact area. If you want to see what that is numerically, we can plug that into a calculator, and we see about 43.5. And since it's area, the units are feet squared. Wow! We actually had to dip into trigonometry to figure out this A in order to find the area. You can see once again a wonderful example that mathematics is totally interconnected, and it's really important not only for us to understand all the different avenues of mathematics because they fit together like little puzzle pieces, but to be able to realize when we have to apply them. Very cool, very surprising. When you first saw the stop sign, were you thinking tangent? I think not. Anyway, congratulations, and think about some trigonometric functions sometimes as you're finding the areas of interesting regular polygons. And I'll see you soon.